this. Uh, so our how do we describe quantum particles, identical quantum particles? How we are going to? So we are going to start with our description of identical quantum particles. Uh, so basically we are going to see जो हमारे पास quantum mechanics में how we see their fundamental जो characteristic property है एक distinguishability है distinguishability and the other is indistinguishability means you can distinguish one set of particles and can not distinguish them vis-a-vis in space जैसे for example if you are two red and white balls are there in the common sense अगर before and after collisions you can distinguish even though they may be of same dimension and length if the color is distinguished the color is different you can distinguish the things अब यही चीज है जो फंडामेंटल डिस्क्रिप्शन ऑफ classical and quantum mechanics. Classical distinguishability is different from quantum distinguishability. Classical distinguishability में ये है कि before you are going to have an if you are going to measure a quantum system before classical system before or after. So you can always, you will be always be able to distinguish particles. That's it. But in quantum mechanics, the distinguishability or जो है because of you cannot simultaneously determine it's basically you are seeing things you are seeing things uh, so you are seeing things in you are seeing things in the sense that जो आपका ये है due to quantum theory जो हमारे पास uncertainty principle है whether how you can identify a particle in measurement. So it has our measurement जो है it's not the way we define measurements in the classical sense. So our indistinguishability for quantum particles which may or may be जो हमारे पास Pauli's exclusion principle है no two electrons can be in the same state or they cannot be in the same state so they can be so you can have particles in the same state or they cannot be in the same state. So if the constraints of Pauli exclusion.
Hello, sir. On your mic, sir.
सर आपकी आवाज नहीं आ रही.
Now it's coming.
हाँ सर अब आ रही है. सर अब ठीक है.
So you can say that you just include everybody in the waiting room जो भी है ना just admit all whoever comes. So you can see जो हमारे पास quantum particle है quantum mechanics में है our indistinguishability is subject to the constraints how we measure quantum mechanics and जो हमारी whether we can use Pauli exclusion principle is it depends upon how we see if you remember आपकी Fermi particles and Bose quantum particles bosons and fermions how we said them fermions and bosons को हम कैसे define करते हैं हम कहते हैं कि जो waves functions है psi a plus psi b so for symmetrization if you have a symmetrization psi a plus psi b should be positive so if you exchange two states psi and psi b if you change तो उनका position अगर आप change करोगे it should not matter for symmetric waves For antisymmetric psi A plus psi B, अगर हम psi A को psi B की जगह करेंगे, so it will be minus psi B of plus psi B. So on that this fundamental property we could classify or distinguish particles either as Bose particles or either as Fermi particles. उनको spin half होता है जिनमें antisymmetric property होती है, and the properties particles which have Bose particles they have spin 1. अब हमारे पास मसला ये है कि जो हमारे पास फॉर एग्जांपल क्वांटम मैकेनिक्स थ्योरी ऑफ आइडेंटिटी पार्टिकल्स जो है, हम वो टॉक देम नॉट ओनली इन टर्म्स ऑफ दीस थिंग्स, वी आल्सो टॉक इन टर्म्स ऑफ ऑक्यूपेशन नंबर, डेंसिटी ऑफ ऑक्यूपेशन, and one particle states normally हम deal करते हैं, and something called second quantization which we see, and how we can generate creation and annihilation operators. So operators we have been throughout seeing operators, whether they are linear operators, so whatever the operators are, तो हम उनकी जो properties हैं operators की, तो on that thing how can see operators acting on states and what do those states give. So we can have creation operators as well as annihilation operators in our state. So creation operators and annihilation operators. So these operators act on different states. So in some states, the states can be ground states or just depending upon occupation number. Ground states में कभी कभार हमारे पास जो for example stationary states भी हम ले सकते हैं, and an operator acting on that state, it will allow that state to go from lower state to higher state or from higher state to lower states. तो अब ये है कि indistinguishability of state vectors for how we say them for identical particles. So we can say जो हमारी description of what I should say, we had a spin polarization states. If you remember, हमने Pauli spin matrices को in terms of P को in terms of sigma लिखा, and sigma was sigma x, sigma y, sigma z. So polarization for this thing, how we could see polarization and so that we could assign these states which are being acted upon by those operators, which will have these indistinguishability as a property. उसको हम कैसे assign करें? How we will see it? How we can see things? अब जिस तरह हमने कल कहा था कि there is a relationship between operators, symmetry and inversion. In the same way, there are some fundamental symmetries in quantum mechanical states, which might correspond to, for example, axis spin है, isobaric spin है, in a high energy physics hypercharge है, symmetry of SU3 है for photon, proton, electron जो भी है, तो या quarks may come out in different flavors, up, down, जो भी है, which maybe we may assign quantum numbers to them. So that's it. So the latitude. So how we can describe the states for identical particles, and then we can see how those particle states how they will act, be formed from the operators जब उन पर act करेंगे, या how we can find states, general states को हम कैसे formalize करेंगे, ठीक है? Those states जो होगी they may be identical, indistinguishable or distinguishable states जो हमारे पास होंगी. So if हम कहेंगे जो इस assumption हमारे पास होगा, any complete set of operators which describes the behavior of a single particle can also be employed for particles of same kind. So you can have these things. So in the before we are going to say how can any combination of operators which describe the behavior of single particle can also be employed in the particle of the same kind. So you can जो states है ना हमारे पास. So how can first हम कोई basis state vis-a-vis whether they are identical particles, उनकी basis states क्या होंगे? How can construct that basis state? But basis state हमारे पास होगा for single particle and particles of the same kind. So एक particles या एक kind of basis states को हम कैसे construct करेंगे? Such that जो हमारे पास eigenvalue होगा, eigenvalue Ki corresponds to occupation numbers and so you can have if they are at identical states with particles of the same kind so which have eigenvalues. For example, हमारे पास initially we had state psi, फिर हमने spin में कहा we have spin states. They will be operated upon by those operators. They will give those eigenvalues. Operators acting on eigenstates will give eigenvalues. अब ये है कि अगर particle of the same kind है of the one particle single particle होगा and particles of the same kind होगा तो उनके eigenvalues कैसे हम have some occupation number उनको हम कैसे reconstruct करेंगे और construct हम कैसे करेंगे such that totality of operators so हम complete set of commutative Hermitian operators. How can have complete set of commutative Hermitian operators? Complete set of such that they are eigen. So this is the thing. So why we will have a complete set of commutative Hermitian operators because their eigenvalues will then be real. Yes. तो अब हमारा काम ये है कि first we have to identify that base space, right? जिसको हम in the mathematics of quantum mechanics हम कहेंगे वो Hilbert space जो होगी वो कैसे उसको कैसे construct करेंगे for this one particle state with the particles of the same kind. उसकी basis state कैसे हम construct करेंगे? Then at the end, when we identify those basis states, whether those will be bosons, whether they will be fermions, वो बात की बात है. That's a separate thing. So first, we are going to अगर हमारे पास कोई vacuum state है, there is vacuum, तो उसमें हम will first have one particle state को कैसे हम how can represent them. So such that जो हम before we are going to represent them, so the point which I am going to say here is so अगर हमारे इसी चीज को हम in the language of what I should say in the language of इसको हम Hilbert space इसी को हम Fock space कहते हैं. What it's called? So which will be basically these single particle space of but particles of the same kind, which have eigenvalues. They might have occupation numbers. And so what are they going to operate, and they can have complete set of permission operators act करेंगे, which will give those realized values. अब इसमें both we can have, for example, if we have this Fock space, इसमें n particle states हैं, n1, n2, n3, so on and so forth. कोई भी basis state है, इसमें n particle state है. अब अगर हमारे पास इसमें, for example, if we only want to take n1 and n2, we can say k1 belongs to n1 and k2 belongs to, for if two particle state, we can have 3 particle state, 4 particle state, and n particle state. So in this today's class, we will begin with what is something called, we'll first start with something called one particle state को हम कैसे represent करेंगे. पहले before one particle state, we something called vacuum state या ground state भी हम इसको कहेंगे. Vacuum state या ground state को हम कैसे represent करेंगे in that sense. So no particle state or vacuum state psi 0 can be written as 0, 0, 0. And then one particle state can be. So we can introduce one particle state, two particle state, three particle state, and n particle state. So we are to begin with starting with one particle state and particles of the same kind. So we can represent that thing as, for one particle state psi I, को हम ऐसे represent करेंगे. Ki is equal to this cat or bra represented by some state, cat state. We can have one particle state as 0, 0, 0, and I. Or we can have one particle state from ऐसे भी represent करेंगे. The other are the ground states, 0, 0, 0. This is Ni. Ni is the number of particles, and the particles of the same kind. इसको फिर हमने मान के साथ represent किया. Yes. Yeah. You can have 0 particle state, 1 particle state, 2 particle states, so on and so forth. अब क्वेश्चन हमारे पास, इसी को हम कहते हैं Fock version भी, and using this bracket notation. अब क्वेश्चन हमारे पास है ये कि does the postulate of this section जो हमारे पास ये postulate है, it provides the ingredients of quantum theory of interacting particles. ठीक है? Here I want to make the basic thing. जिस तरह हम mechanics में है ना, we start with something called frictionless thing. Harmonic oscillator लेते हैं frictionless, है ना? Then we add those damping terms, ठीक है? But जो friction term है, in principle जो nature में friction होता है, ठीक है? In the same way हम लेते हैं tensionless string, या जब हम linear harmonic oscillator में लेते हैं फिर higher order terms for all the oscillations. In the same way जो हमारे पास ये है, this is a free field theory. This is not an interactive. जो हमारे पास quantum field theory, normally advanced quantum mechanics में, we normally talk of free field theory. But the thing is, we have interacting systems. So अब उसमें हम use करते हैं, we take recourse to perturbation theory. Okay, we take perturbation along some stable or minimum, and then see perturbations around that stationary state, and including those higher order terms. So in the same sense, what we are going to see here in the so in the same sense, we are going to use जो हमारे पास once we go to interacting theory, we are going to, or interacting quantum field theory, we are going to use in the जो lifting case में one particle state या कोई ground state में वो वाली term लेंगे, And we can to account it or account for the experimental observations, we can see perturbation along that minimum kya aayega and account for those very things. And we have a proper theory of renormalization where we can account for those higher order interactions. Depends upon हमारा जो experimental settings कैसे होंगे, how we optimize our empirical parameters, because these states, जो हमारी ground state है, it should, if it's a single kind, it should ultimately describe some system, bosons, fermions, ठीक है, जो भी है हमारे पास. तो अगर ऑफ द वन काइंड है तो fermions है या bosons है तो one particle state है, इन्हीं के फिर ऑपरेटर्स एक्ट करेंगे, जो ग्राउंड स्टेट के बाद ऑपरेटर इट विल गो फॉर नेक्स्ट टू नेक्स्ट स्टेट. सो ऐसे ही हाउ कैन सी थिंग्स. So even if we have a freak theory or if we have a non-interacting theory, but you can use non-interacting theory and have some additional things to incorporate a quantum theory of interacting particles. So even though we have identical particles, we can have interacting particles. Or interacting particles में जो identical particles हैं, they can come as a limiting case of those particles, identical particles. अब इसमें at the end we will just see something called creation and annihilation operators. So creation and annihilation operators means, for example, for a given species of particles, हमारे पास तो creation operator को हम a dagger से denote करेंगे. So a dagger acting on n1. These are different one particle states, two particle states, ni minus one states, ni plus one, so on, so forth. They can, so creation of this a dagger can act on this state. So if it acts on ground state, it will give उसके ऊपर वाला state. If it's upper state, it can. So you can see adding a basic state. So from the definition of permutation, so इसी तरह ये भी creation operator, इसी तरह annihilation operator को ऐसे denote करेंगे. And one and two. Creation and annihilation operator में सिर्फ इतना फर्क है, it's the अगर वो एक state को ऊपर करेगा, ground state से ऊपर जाएगा, वो annihilation operator उसको नीचे लाएगा. This is the thing how we can say it. And so for the sake of simplicity, we can say that we can say that a dagger psi 0 is ai dagger psi 0 psi I. So you can say a state acted upon by ground state, it will do 0. So any operator acting on ground state or vacuum state, it will give the vacuum state back, just like multiplying something by 0. So so you can say that a dagger of psi is ai dagger psi 0 is psi that I 1. Its ki state is 0 n minus ni for one particle state. It's like this. In the same way, ai, this is creation operator. Now, this is an integration operator acting on state psi I is AI, KJ is equal to AI 0, 0 and 0. तो अब इसमें से ये है it will be delta IG psi k. So the question is how creation operator and deletion operators act on these ground states. That's the point. And one particle states also. So this was our description of how we can describe identical particles in our today's class. And we are going to continue our discussion of how we can, for example, if we have an arbitrary one particle state, we can just see, we can continue after this, we can have this algebra of these creation and annihilation operators in our next class, so that we can continue our discussion. Okay, we'll stop.
Yes, sir.
Okay, you have to ask anything?
No, sir.
Chalo, ठीक.